Hello, I'm Jeff, and today we are going to be taking a look at an introduction to limits. Boy, doesn't that just sound like a joy, which is the very first step to conquering the great beast of calculus. That reminds me more of an ant's antennas than a horned demon, but surely you knew what I was going for, alright? Don't give me grief, it's fine. Okay, so first we need to ask ourselves the pretty fundamental question of what is a limit? Well, that sounds pretty important, so let's go ahead and throw in a definition. Well, a limit is effectively the value that a function, so f of x, is approaching as x becomes infinitely close to a certain value. Okay, great, excellent. But what does infinitely close actually mean in a mathematical sense? How do we express this in terms of numbers? Well, considering this relates to the field of math, that seems like a pretty important question. So let's go ahead and work through an example to try and figure this out. So let's say that x is approaching some arbitrary value 3, for instance. Well, we can say that x is equal to 2.9, or we could say that x is equal to 2.99, or we could even state that x is equal to 2.99, and then just however many nines you want to throw in here, really. The whole point is that x is getting infinitely close to 3 without ever reaching it. We could express this in 100 nines or even 1,000. I mean, we could express this with as many as we want because x is getting infinitely close to 3, but never being equal to 3. And that's a very important distinction to make, is that x is never going to actually equal 3, no matter how close we get to it. And we're going to see why this is such an important distinction to make as we actually get into solving a few problems. So, without further ado, let's go ahead and dive right in. All right, so we have question 1 here. What is the value of f of x as x approaches 5? So we have y is equal to x plus 2. That gives us a simple linear function. And let me tell you, in calculus, linear functions are like an utter unicorn. So I recommend that we all take a moment to savor this before we move on. Well, returning to the question itself, we have f of x as x approaches 5. And we can recognize this from what we covered earlier as being effectively a statement of a limit. So what we're evaluating here is the limit of f of x as x approaches 5. So let me just write that down really quick. Lovely. Isn't that much better? Now, all we have to do is evaluate this function, x plus 2, as x becomes infinitely close to 5. That's what a limit is. So the only difference between what we're doing now and what we did previously is that this is in the context of a function. And that might seem a little daunting, but if we just break it down, it's actually pretty simple. All right, so let's get right into this. So as x approaches 5, we can go ahead and say that this function, as x is equal to 4.9, is going to equal, we just add 2, that gives us 6.9. Nice, hilarious. And then as we continue down, we can say that we have 4.99, and that's going to give us 6.99. And then finally, if we say that x is equal to 4.9 and then just however many nines, that's going to translate over to 6.9 and then however many nines we added to the x. Awesome. So what does this actually mean? Well, we can observe that as x becomes infinitely close to 5, this function is becoming infinitely close to 7, which makes a lot of sense considering the function is just x plus 2. So this is all trending towards a specific value, 7. And what that means is that we can actually go ahead and say that this all evaluates to just, well, 7, because that's what the function is approaching. And we can notice that if we actually look at the graph here, we have x is equal to 5, and that, well, looks to be 7. You can also see that we're approaching 7 from both sides of the function. And, well, that makes a lot of sense. If we were to try x is equal to 5.01, for example, well, that's going to give us 7.01, which is ultimately trending in the same direction towards the specific value of 7. Now, you might be wondering, hey, did you say not 1 minute ago that although x is becoming infinitely close to 5, it's never going to precisely equal 5? So in that case, how can we say that the limit of x plus 2 as x approaches 5 is equal to exactly 7? That seems rather odd. Wouldn't that just be 5 plus 2? And well, the reason we can say that is because remember, the limit isn't the exact value of x plus 2 when x is equal to 5. It's the value that the function of x plus 2 is approaching as x approaches 5. If you're still a little confused, no worries, because as we jump to the next few problems, we're going to explore the idea of continuity, and it's there that the difference is going to become glaringly apparent. Trust me. Now, before we tackle the next problem, we need to figure out some new notation. Now, you may have seen this before, you may not be familiar with this, and I know it might look very daunting at first glance. I can imagine seeing this on a test and just hearing alarm bells blaring in your head trying to figure out what on earth you're supposed to do with this, but it's actually pretty simple. This is really just another way of expressing a limit, similarly to what we just did in the previous problem. We have the limit of this function, x minus 3 over x minus 3, as x approaches 3. That's it. It's really that simple. Unfortunately, this whole scary notation thing is going to be a pretty common theme throughout calculus, and I'm afraid I can't promise they'll all be quite as easy as this one. But at the very least, we can go ahead and move on now that we're aware of what this actually means. All right, so now let's go ahead and try to solve this. So just looking at this, it seems that for any value that we plug into this function here, we're just going to wind up with 1. And we can test that really quickly. So let's see. Let's try 5 minus 3 over 5 minus 3. And well, that's just going to get us 2 over 2, which is equal to, let me pull out my calculator. Oh, right, 1. Okay, great. So this seems pretty simple. Substitution worked for us last time, so we might as well try that. That should just get us 1, no problem, right? So we try 3 minus 3 over 3 minus 3, and that gets us, now hold on. This gets us 0 over 0. What are we supposed to do with this exactly? Well, unfortunately for everyone involved, really, this is known as indeterminate form, 0 over 0, and you can bet it's going to be a common nuisance throughout your study of limits. Now, the reason this is called indeterminate form is because the value of 0 over 0, well, it doesn't actually exist. Dividing by 0 just results in undefined. Now, that might seem a little bizarre to you, considering as how mathematicians have had over 2,000 years to figure this out, but no, apparently I'm the one who procrastinates. Well, anyway, trying to think about this from a sort of intuitive perspective, it does make a degree of sense, admittedly. If we tried to take 0 divided by 0, one could argue that something divided by itself should just equal 1, but at the same time, one could also argue that if we take a number like 5, for example, and divide it by a small number like 0.001, well, we're going to wind up with a pretty big number. So if we take a number and divide it by 0, we should wind up with an infinitely large number. That does make sense, and considering as how there's a modest gap between 1 and infinity, it's a little bit difficult for mathematicians to come to any sort of clear answer about the topic. So for now, we just say undefined and call it a day. All right, cool. So we tried to use substitution and we came up with nonsense. So we can say that f of 3 is equal to undefined. So is that it? Does that mean we can't actually solve this limit? Does this limit have no value? Is it undefined, just like f of 3 is? Well, no, because if you remember, the value of f of 3 is entirely irrelevant. So we have x is equal to 3, and here this is going to be undefined. But the limit is simply the value that the function approaches as x approaches 3. So it's only the values leading up to 3 that actually matter. So if we were to try, for example, 2.9 minus 3, divided by 2.9 over 3, and I'm just plugging 2.9 in, we get, well, 1, because that's 0.1 over 0.1, and of course you have the negative signs that just cross out. So that gives us 1. And if we were to try 2.99 minus 3 over 2.99 minus 3, well, that just gives us negative 0.01 over negative 0.01, which is once again equal to 1. So, and this is just reusing the same technique we used earlier. We're getting infinitely close to 3, and we keep winding up with 1. So we can go ahead and say that for this limit, as x becomes infinitely close to 3, this limit is just approaching 1. And, well, we can see that. We can see that this is just going to continue equaling 1 for the entire time. Although 3 might be undefined specifically, the function as a whole is equal to 1. So it doesn't matter. So we can just write that this limit is equal to 1. Isn't that interesting? All right, so we have our next problem here. Question 3. What is the value of the limit of x cubed minus 2x over x as x becomes infinitely close to 0? All right, well, this is quite clearly a little hairier than our previous problems, but not to fret. We have strategies to solve this now. So if we just go ahead and try substitution, so we plug 0 in for all of the x's, that's just going to, well, quite clearly give us 0 minus 0 over 0, which is, what do you know, indeterminate form. Again, so that means we're going to need to use something else to solve this. Now, we could just use basic substitution and try plugging in x values as x becomes infinitely close to 0. So we could try f of 0.1 or f of 0.01. That is the completely wrong thing. Oopsie. But ultimately, there are more mathematically sophisticated ways to solve that. So why don't we try exploring another avenue? Now, we can use some simple intuition to solve this. So, we have x cubed minus 2x over x. Well, if x is equal to 0, then this is going to be undefined because, well, we're dividing by 0. So, what if we were able to factor out this x somehow? Well, luckily for us, this is actually a pretty simple function because we can simplify it. You see, we have an x term and we have another x term. So, we can take x third 2x over x and simplify it to just x squared minus 2. Now, what's so useful about this function that we've just derived is that it's virtually identical to its parent, except for its behavior at x is equal to 0. And that's because, well, this one isn't dividing by x. It's not dividing at all, which means we're never going to encounter dividing by 0. And that means that we can go ahead and apply this function to determine the value that this function is approaching at 0. Or in more mathematically rigorous terms, we can say that the limits of x cubed minus 2x over x as x approaches 0 is equal to the limits of x squared minus 2 as x approaches 0. Now, isn't that beautiful? And then we can solve this limit using simple substitution. So if we take x is equal to 0, well, that's just going to give us 0 minus 2, which is equal to, obviously, negative 2, which means this entire limit just evaluates to negative 2. And when we observe this graph, we can actually see this undefined behavior at x is equal to 0. We have this little hole in this function, and this is called a removable discontinuity. All right, looks like we're done here. No need to delay. Let's move on to the next. All right, we have question 4. What is the value of... Oh, jeez. All right, well, this looks like a bit of a mess. Let's try and figure this out. So first, let's just completely ignore this and try to understand what this actually means. Now, if you're unfamiliar with this notation, this is called a piecewise function. And a piecewise function is unique in the sense that it's effectively a function that's divided into multiple functions. And the version of the function that we're going to use is dependent on what the value of x is at a certain point. So let's say, for example, that f of 5. So first we need to determine which version of this function we're going to use. So let's take 5. So we see that when x is greater than 1, we use x minus 3. Well, last time I checked, 5 is greater than 1, which means we're going to use x minus 3. So we take 5 minus 3, and that gives us 2, of course. And just looking at this function visually, that looks to be about right. So this seems to be about 2. Now, what about when x is less than 1? So let's say we want to find when x is equal to 0. So heading up here, when x is greater than 1, we use x minus 3. Well, this isn't true for this particular x value, so let's go down here. So when x is less than 1, we use negative 3x plus 1. Well, 0 is less than 1, which means we use this. So we plug x into this, which gives us negative 3 times 0 plus 1, which is just going to be equal to 1. Beautiful, which means that f of 0 is equal to 1. And observing it visually, we can see that, yeah, that looks to be about right. So awesome. Now that we have a basic conception of what a piecewise function is, let's go ahead and get into solving its limit. Now, it appears we need to solve the limit of this function when x is getting infinitely close to 1. But I'm almost glad to reveal that this function doesn't actually have any defined behavior at x is equal to 1. We have when x is greater than 1, we have when x is less than 1, but never when x is equal to exactly 1, which means the value of this function at x is equal to 1 is just going to be undefined. Okay, great. So now what do we do? Well, remember, the value of f of 1 is entirely irrelevant. All we need to know is what the value of this function approaches as x becomes infinitely close to 1. And the way we can determine this is by just plugging the value that we're approaching, 1, into both of these to see what they're approaching. So we can take x minus 3 as 1 minus 3, which gives us negative 2. And we can take negative 3x plus 1, and we get negative 3 plus 1. And that's equal to, well, negative 2, which means that from both sides, we appear to be reaching the exact same value. So even though f of 1 is itself undefined, both sides, it's approaching the value of negative 2. So that's our answer in that case. So this entire limit evaluates to just negative 2. And looking at this graph, we can see that at this value, f of 1, we have yet another removable discontinuity. So that's it. We seem to have solved this one. On to the next. All right, so throughout the video, we've covered a few limits, and I don't think they've been that bad myself. You may feel differently, but hear me out for just a moment. What if things got worse? What if things got more complicated? Doesn't that just sound fun? I'm sure that's exactly what you've been asking for all along. So now we're going to explore when a limit doesn't exist. It doesn't have any value that we can actually come to and say it evaluates to. So we have question 5. What is the value of the limit of 1 over x as x becomes infinitely close to 0? Now, if you're perceptive, you may have noticed some unusual behavior from this graph compared to the others we've seen. So we can notice that as x becomes closer and closer to 0 from one side or the other, the function just kind of jumps to the other. And, well, this is part of the reason why this function doesn't have a limit. And what do I mean by that? Well, let's go ahead and evaluate this mathematically. So just looking at this, if we try to substitute in 0, we're just going to get division by 0. That doesn't work. So let's try evaluating this as x becomes infinitely close to 0. So we have x is equal to 0.01. Well, this is going to be a pretty big number. That gives us 100. And if we try 1 over 0.001, well, that's going to give us 1,000. So what we're observing here isn't a trend towards any particular number, but actually to infinity itself. And the reason for that is because as x becomes infinitely small, this value is becoming infinitely large. So we'd say that this is bounding towards infinity. But what about down here? Well, we are going to get, as x becomes infinitely close to 0 from this direction, negative 0.01, which is going to give us negative 100. And if we keep going, that's going to give us negative 0.001, which is negative 1,000. So what we're seeing here is, in this case, a trend towards negative infinity, which means that we'd say this is going to be bounding towards negative infinity. And since these aren't converging in the same direction, there is no limit. We would say that this limit does not exist, or DNE. All right, folks. Looks like we've got another hairy one. Question 6. What is the value of... I am not reading all of this out. So instead, let's go ahead and examine some of the behavior and break this down. So when x is greater than negative 1, we have what looks to be the behavior of a quadratic, or at least half of one. And then when x is less than or equal to negative 1, we have a simple linear function. So we're trying to evaluate the limit of this function as x approaches negative 1. All right, well, at first glance, this doesn't actually look too bad. I mean, in this case, the function actually has defined behavior when x is equal to negative 1, which means that the value of this function at negative 1 is just going to be, well, we plug in negative 1, that gets us 3 minus 4, so negative 1. So is that the limit of this function? Well, no. It's never quite that simple, is it? No. You see, the reason is because we're approaching the value of -1 from this direction. That is certainly true, and we can observe that quite clearly. But the important thing about a limit is that a limit has to be approached from both directions. And when we see this behavior here, we can notice that from this part of the function, we're approaching an entirely different value at -1. So if we were to plug -1 into this, we'd get 1 squared, which is just equal to 1, but that's not even anywhere near -1. So that means that from this side of the limit, we're not approaching -1. And in that case, the limit does not exist. So this is another one that we'd say DNE. And what's interesting about this one is that -1 does actually exist, but the limit does not. And this is another way of highlighting the disconnect between the actual value of -1 and its limit at -1. So this is just something very important to keep in mind. And you might be wondering if this has a particular name, just like the other discontinuity, and it just so happens to. This is called a jump discontinuity. All right, before we wrap up for the day, just a few things to keep in mind. Limits are going to be crucial to understanding derivatives later on, so I recommend you get a strong understanding of them both mathematically and intuitively. Otherwise, you might feel a little lost. And another thing to keep in mind is that limits are very prominently featured in AP Calc exams. So if you're planning to take either the Calc AB or Calc BC exam, I sincerely recommend you do some deep diving into limits. Otherwise, you might get tripped up by a couple of tricky questions. All right, well, with that complete, thank you very much for watching, and please like, comment, and subscribe if you enjoyed. Thank you kindly, and have a wonderful day.